tardes. Bienvenidas y bienvenidos al Seminario Fronteras de la Energía, organizado por el Instituto de Energías Renovables de la UNAM. Agradecemos a todos y todos su presencia en este nuevo año del ciclo de seminarios de Fronteras de la Energía. Y hoy tengo el gusto de presentar al profesor Johannes Schiffer, que nos acompaña de la Universidad de Tecnología de Brandeburgo en Cottbus-September. A continuación voy a hacer la presentación del profesor Johannes Schiffer y la voy a hacer en inglés. Professor Dr. Engineer Johannes Schiffer received a diploma degree in engineering cybernetics from the University of Stuttgart in Germany in 2009 and a PhD in electrical engineering from Technische Universität Berlin in Germany in 2015. He currently holds the chair of Control Systems and Network Control Technology at the Brandenburgische Technische Universität Cottbus-September in Germany and leads the Business Area System Integration, Automation and Operation Management and the Fraunhofer Research Institution for Energy Infrastructures and Geotechnologies. Prior to that, he has held appointments as lecturer at the School of Electronic and Electrical Engineering in the University of Leeds in the United Kingdom, and as research associate in the Control System Groups and the chair of Sustainable Energy Networks and Sources Energy, both at Technische Universität Berlin. He and his co-workers received the Automatica Paper Prize over the years 2014-2016 and the IT Automatisierungstechnik Best Paper Award 2022. His current research interests include the development of control engineering methods for complex and interconnected dynamic systems and their applications to practical challenges, in particular, to increase climate neutrality in industry and society. Professor Johannes Schiffer, thank you very much for accepting the invitation to participate with us, and you may start with your seminar.
Right. Well, first of all, thank you very much for the invitation and also for the kind introduction. And I think the topic that I would like to discuss with you today pretty much fits into what you described as my research interest at the very end. So it's like a combination of some new developments that are more control theoretical with an application in the power systems area. And this is joint work with a number of people, some of whom you may actually know, but most of the work is actually due to a former PhD student of mine, Nikolai Lorenz Meyer. And then it is joint work with Juan Rueda Escobedo, that you all, of course, know, as well as Jaime Moreno, who is also with UNAM, and three more people at my group in Cottbus, namely Rolando Cortés Martinez, Ria Matthew, and Eric William Zurita Bustamante, who have mainly also contributed to the recent experimental implementation and demonstration of the algorithm that I would like to discuss with you. But before sort of jumping into the technical part, I wanted to give you a bit of a background information that motivates this work, and in particular also motivates why we are conducting this type of research in Cottbus. So what you can see here is like a map of Germany with the three main coal districts. And Cottbus is located here in the Lusatia coal district and has been for decades one of the three main powerhouses in Germany. So we have a lot of tradition and history in coal and particular lignite mining, and also a number of very large-scale power plants that are in our close neighborhood. And if you zoom in somewhat closer into that Lusatia area, you see the two cities, Cottbus and Senftenberg, that host the university. And between that, you see a lot of like small blue dots, and all of these dots are artificial lakes that are formed by former coal mines. And certainly also a lot of the wealth and economic and industrial infrastructure in the region is currently still based on coal mining and lignite mining. However, the German government has decided to fade out all power generation from coal at the very latest in 2038. And that, of course, also now poses a quite significant challenge to the three remaining regions that you've seen on the initial chart, in also transforming their own local industrial and economical infrastructure. And this is something that we are now able to accompany from the university side where we have launched about 4 years ago a new Energy Innovation Center with the objective of transforming the current lignite-based energy and industry infrastructure in the region into a more climate-friendly and ideally climate-neutral future energy model region. And for that, in the Energy Innovation Center, we have 6 different labs that focus on different aspects that are relevant to the development and implementation of integrated and sector-coupled energy systems, from the economics part over storage and conversion, scientific computing, power electronics architectures, of course, also traditional electric power systems, and last but not least, control systems and cybersecurity aspects. And the overall center is supposed to be established over a time period of 10 years, and we are currently approaching the end of the first year. And we have 15 professors from the university that are involved with the center, and over 80 academic and technical staff members, as well as over 50 student research assistants that support us in our different research activities and projects. And at the moment, we are preparing the application for the second phase, where the development should also, like the focus should be more strongly on product-oriented technology development. And this also means that we have more actively and closely engaged with over 20 industrial partners who will also support us actively in the second phase of the project. Of course, in parallel, we still aim to further establish excellence in fundamental research. Right, and this is an overview of the different industrial and also scientific partners that support us in the consortium. And you can see it's a mix of small, medium-sized enterprises, mainly from the Lusatian region, but also of large national, international players, both on the industrial side as well as on the research side. And overall, these sort of changes that are imposed by the policy making on a federal level with the termination of coal-fired power generation also has led to a lot of new developments in the Lusatia area, and in particular in Cottbus, with quite a number of different research projects and also new institutes, for instance, from the DLR, so the German Research or Aerospace Association, as well as from the Fraunhofer Society, that now have opened offices and institutes here in the Cottbus area, so that at the moment we have around about over 1,000 researchers that are working here in different areas related to energy. And that, for the size of Cottbus, which is a city of like 100,000 people, is of course a quite substantial work and research force. And in this sort of overall landscape, also the more technical aspects of the talk that I would like to present today are sort of centered. And as many of you may of course know, state estimation and power system is nothing new. Particular static power system state estimation has for a very long time been an essential part of power system monitoring and control. However, if you look at the developments that we have seen over the past 2 or 3 decades by now, we have a massive introduction of power electronics interface components and also new demand response technologies, more complex load behavior, and in combination with the higher variability and fluctuation of renewable energy generation that typically leads to an operation of the power systems at higher loading. And as a consequence of that, it also means that the situational awareness of power system operators needs to be focused more towards also the dynamic or transient behavior, rather than as traditionally a purely steady state behavior. And at the same time, of course, this new, more dynamic behavior of power systems also imply that the conventional steady state assumptions that have been used for static state estimation are questionable, at the least in future power systems. And that sort of motivates the increasing relevance of dynamic state estimation. And you can see, for instance, here on the left, so there's a dedicated task force from the Power Systems Society that looks in particular into relevant aspects and topics of dynamic state estimation. So it's also a topic that is not only relevant in the control systems community, but that is really a quite intensive area and field of research also in the power systems community. And one of the key parameters in power system operation is the so-called inertia constant. And therefore, a lot of attention has been dedicated to derive algorithms to estimate the inertia constant in power systems. Right? And what you can see here on the top is a chart where you see the system frequency response following a perturbation for different inertia constants. And you see that in particular, the value of the inertia constant significantly affects the rate of change of frequency following a perturbation, and as such is a crucial parameter to ensure overall system stability, or at least to have a good understanding of what stability risks may occur. And this becomes increasingly important in systems where we have a large amount of power electronics interface units, because traditionally large generators would provide inherently inertia to the system via their rotational mass. And if we now replace that rotational mass with power electronics, of course, we also lose the inherent inertia that we have in the system. And that implies that online estimation of the power system inertia is becoming highly relevant for system operators. On one hand, from really like a operational and stability aspect, but also from an economic aspect, because for instance in the UK, but also now in Germany, they're introducing new ancillary services in the context of fast frequency response or virtual inertia provision. And of course, then if the TSO has the responsibility of securing that there is a certain amount of inertia available in the system, they also need to have tools that allow them to monitor that inertia constant. And well, this fact has led to a very large, I would say, amount of different research efforts that try to provide estimation algorithms for the inertia constant. And you can broadly class them into three different categories: offline estimation, online estimation, as well as forecasting approaches. However, what all of them have in common is that they take a central perspective. So the objective is to estimate a single inertia constant of an overall large-scale and interconnected power system. Yet if you look at reality, then in particular in the European context, but also, for instance, in the American context, power systems are typically multi-area systems that are operated by a number of independent transmission system operators, and each of them is responsible for their own separate control area, right? Which is what you see here in the figure on the right-hand side. And if you then want to estimate the total inertia for this interconnected European power system, for instance, this would require measurement data from the entire system, and as a consequence, it becomes imperative that the different transmission system operators also collaborate and cooperate between each other. And well, this is sort of the setup that motivates the contribution or the main technical results that I would like to convey. So what I want to do is to present a distributed algorithm that can address the problem to estimate the inertia constants of the different areas in an interconnected power system online, and that can also do that in the presence of typical disturbances, so for instance, load variations or other type of perturbations that you would typically find in power system operation. And we're going to tackle that problem by at first deriving a set of linear regression equations that are based on the so-called center of inertia dynamics for each control area in the multi-area power system. And then I'm going to introduce a robust version of a consensus and innovation distributed parameter estimator together with a tuning method that provides the desired robustness. And then I'm going to show you how it performs, first via simulation based on the New England IEEE 39 bus system, and then also via an experimental implementation in a power hardware in loop setting where we use 5G as a wireless communication network or technology to enable this distributed estimate. So with regard to the multi-area power system model that we use for the inertia estimation, we employed the so-called center of inertia dynamics for each power system area, which is given by this first order differential equation here, where omega I is the frequency that you have in the particular ith area of your interconnected power system. And you obtain that essentially by aggregating the dynamics of all the different generators that you have in the system, or more generally, all the different entities or units that contribute to frequency control, right? So traditionally, this was derived by aggregating the swing equation dynamics of the different synchronous generators in the network. However, as we will see later also in the experiment, if you have grid forming inverters that are controlled, for instance, as synconverters or virtual synchronous machines, they obey, of course, the same dynamics in closed loop as traditional synchronous generators, and can then also be captured and included in these aggregated center of inertia dynamics. Omega 0 here is the nominal frequency, as B denotes the total rated power of the area, and HI here is the total inertia constant of the ith area that you obtain by summing by aggregating the different inertia constants of the units in the power system. Right, and delta PI is the power imbalance, so deviation between the injections and the demand that you have in the system. This is how it looks in a block diagram. So we have here our differential equation, and the parameter that we would like to estimate is the overall inertia constant of our ith area. And the question is now, do we have all the required measurement information? And typically what you can assume is that, of course, you can measure the frequency at all generators in the system, in particular if they depend or they contribute to load frequency control. We can also measure the overall mechanical power that is provided by the generators. And if the generators are contributing to primary frequency control, this is typically also a quantity that is available. And what is, of course, not available explicitly is the overall power demand from the grid, because that is something that, of course, cannot be measured exactly. And something else that we have to address is that in the exact center of inertia model, the coil frequency depends as well on the overall weighted sum, or weighted sum of the different frequency variables in the system. And these weights are exactly the inertia constants of the generators. And these quantities, of course, we don't know because we exactly try to estimate them. And therefore, what we do is to replace this exact center of inertia frequency simply by the average frequency that we obtain from all the different generators that are connected to our ith area. And we can, of course, also then do the same for the overall, like the same aggregation for the overall power system. So in this case now for the overall interconnected European transmission system, for instance, and then we obtain the same type of dynamics. But we have then, of course, here the overall inertia constant that now is the inertia constant contributed by all the different areas in the interconnected power system. And if we take now our approximated center of inertia frequency dynamics, we can use them to derive a so-called linear regression equation, which is typically the starting point to derive any type of dynamic estimator or dynamic filter in order to identify parameters. And in order to obtain such a linear regression equation from this differential equation above here, we introduce a second order filter, f, with two parameters, lambda 1 and lambda 2, where s denotes the Laplace variable. And then we can multiply our ODE with this filter and obtain the following relation here for each of our areas that we can now sort of write in the standard form that you would have in parameter estimation problems, where Ci bar here is your regressor and theta I is the parameter that you would like to identify or like to estimate. And in our case, of course, theta I contains the inertia value that we would like to identify. And if you now look at the overall interconnected power system, then for each of the areas that we have in our system, we have such a linear regression. So we have such a regressor Ci, and we also have measurement information locally, Yi. And what we now would like to solve is an estimation problem where each of the transmission system operators estimates not only their own inertia constant, but also the overall inertia constant of the interconnected power system, and as a byproduct, the inertia constants of all the different other power system areas that are contained in the interconnected system. Right, so you see the schematic sort of down here, exemplified with 3 different control areas. And we have 3 different system operators. And the idea is now that we would like each of these operators to exchange as little data as possible. And in particular here, the idea is that the only thing they exchange between them is the estimated value of the different inertia constants that they obtain from their local estimation process, right? So that it's also really an approach where the different TSOs need to disclose as little information as possible to neighboring transmission system operators. And in order to solve that problem, we're going to employ a robust version of the so-called consensus innovation-based distributed parameter estimator. And this is an estimation algorithm that can not only be used and has not only been used in power systems, but is in fact a type of algorithm that is applicable in a large variety of modern engineering applications, because typically you have a fairly large number of sensors, and what you would like to do is to identify a certain set of global system parameters, and this identification typically requires to collect and process information from all the different sensors. And you could of course do that in a centralized way, but that usually requires more energy and also communication capabilities. And of course, you introduce a point of single failure. And compared to that, in a distributed processing, you have improved resilience to failures, and of course also improved privacy and secrecy or security considerations. You can use swarm intelligence in the sense that different sensors also drive the desired behavior. And for these type of distributed processing, there are diverse methods available in the literature, for instance, diffusion, but also consensus-based strategies. And from a more methodical point of view, the type of problem that we're looking at here is that we have a network with n different sensors. And for each of these different sensors, we have a local linear regression equation. And we can now stack all of these different regression equations to obtain the global linear regression equation of our system, where these are here y1, y2, up to yn. So this is the measurement information that we have. C1 to Cn is the different regressors. And theta is the overall parameter vector that we would like to estimate at all sensors in our network. And for this type of problem, a algorithm that is often used and widely promoted is the so-called distributed consensus and innovation-based parameter estimation approach that has been introduced first by Carr and Hora in 2013 and obeys the following dynamics here, where theta I hat denotes the estimate of the ith agent or the ith sensor of the overall parameter vector. And in this setting, we of course need communication between the different sensors, and the topology of the communication network is modeled here by an undirected and time-dependent graph, as you can see sort of sketched here on the right-hand side with different nodes and then different edges that illustrate which node or which sensor can exchange information with which other sensor. And the algorithm is called consensus and innovations approach because it has exactly these two parts. So the last part here is a consensus element or consensus part, where you look at the difference between the estimates at neighboring nodes theta I hat and theta j hat and try to minimize that. And the first term takes into account the innovation aspect, so the new measurement information that you obtain from your regressor. And essentially what one needs to prove that this algorithm works in an ideal setup is a persistency of excitation condition, which is inherent to any type of parameter estimation algorithm. And in this case, since we have a distributed application, and what we need is a so-called cooperative persistency of excitation condition, which is given by this inequality down here. Right? And essentially, you can think of this persistency of excitation in a sense that the measurement updates or the information that is contained in the signals that form your regressor CI, that this information needs to be rich enough for you to be actually able to identify the unknown parameters in your system. However, if you look at real applications, such as we are doing in the power system context, then most often you're not faced with the ideal situation that I described on the previous slide, but instead you have parameter variations, you have measurement noise, and you also may have disturbances in the communication channel. So you have a setup that is far less ideal compared to what we have presented earlier on. And this is something that Nikolai, supported by Juan, addressed in his PhD thesis. And what they did is to introduce a disturbance vector delta to then be able to sort of incorporate these different perturbation effects in the overall CNI-based parameter estimation setting. I'm not going to go into details on the chart down here. Mainly what is important is to understand that, or like to highlight that because of the distributed nature of the algorithm, part of the perturbations, in particular when it comes to the perturbations in the communication channel, are propagated via the oriented, or like their propagation can be described via d bar, which is the oriented incidence matrix of the graph that describes the communication topology. And a first sort of contribution now in this context from the talk today is to provide a robust tuning procedure in the presence of disturbances. And the robustness is cast here as an L2 gain tuning. So what we are doing is to consider a network with a number of n arbitrary sensors. And each of these sensors has the local linear regression equation. And overall, we have a C plus I based distributed parameter estimation algorithm. And now what we want to do is to derive conditions for the gains of the algorithm that ensure that we have overall an L2 gain less than or equal to the square root of gamma. Yeah, and I mean, the L2 gain in control systems engineering is I would say, standard measure to quantify robustness of a dynamical system with respect to exogenous disturbances. And in the linear case, you can relate that to the H infinity norm of your transfer function. Right? So if you're familiar, for instance, with H infinity control, then what you try to do there is exactly to minimize the L2 gain of the overall resulting closed loop system. And well, we are tackling this problem by at first recasting the aerodynamics in the form that is induced by the classical gradient descent algorithm. And that sort of builds the basis to then construct a strong Lyapunov function that is based on the previous results of Juan and Jaime. And this we can use then to develop a design criterion based on linear matrix inequalities that allows us to numerically very efficiently optimize the algorithm's gains. This is now the sort of formulation of the overall tuning synthesis. And for that, we introduce the global parameter estimation error, so the deviations of each of the local estimates theta I hat from the true parameter vector theta. And then we construct the global aerodynamics that you obtain explicitly or directly from the C plus I based algorithm. with the different perturbations that I described earlier. And we then also extend the output error on one hand to include YA, which is the stacked local, the stacked vector of local output errors, and YB, which denotes the estimation errors across different edges in the communication topology. And then we can recast the aerodynamics in this standard form down here. And this is sort of the basis to then obtain the following result, which states that if we have our C+I-based distributed parameter estimator, then the origin is a globally exponential stable equilibrium point, and we have a corresponding quadratic function, which is a strong Lyapunov function for the equilibrium point of our aerodynamics. And strong Lyapunov function means that we have a Lyapunov function whose time derivative is strictly decreasing over time. And this is sort of key to be able to provide afterwards a robustness analysis, but also, for instance, to be able to establish other properties in terms of input to state stability, for instance, also the calculation of analytic convergence bounds. And in order to now arrive at a tuning criterion, we use the strong Lyapunov function as a storage function, define a performance output that takes into account, of course, the output of our aerodynamics, as well as the disturbance. And we then define a corresponding supply rate and try to make sure that, try to define conditions such that this dissipation inequality here is satisfied. And this then can be formulated or cast as an LMI problem that can be solved numerically quite efficiently, and sort of summarized here more technically. But what it boils down to is that you have a SDP, so a semi-definite program, where you try to find the minimal L2 gain, so the minimum value of gamma, subject to certain constraints that are cast here as LMIs that depend on the parameter of your algorithm. And then in the end, you get a bound or like a certain interval where you can choose the overall gain of the consensus and innovation approach. And that guarantees then that your overall error system has an L2 gain that is bounded by the square root of gamma. And I would like to illustrate now how this tuning procedure performs, at first by an academic example before we move back to the power systems application. And what we consider here is an example of 6 identical mass spring damper systems that are connected here via a communication topology. And what we now want to do is to estimate the different parameters K1, K2, and K3. And this we can formulate again as a linear regression equation, and then, of course, apply our consensus and innovations algorithm. And we have done that for 5 different scenarios, and following sort of like different tuning procedures and different gain selections. And I think sort of the key message is that the gain that we obtain, or like that our tuning method obtains or provides, is at the same time also a good trade-off between the convergence speed of the algorithm and disturbance attenuation. Because you can think of it, if you choose the gain of the algorithm very small, then the convergence will be rather slow, but you will not be that strongly affected by disturbances in general. If you choose a very large gain, the convergence in the ideal case is faster. But if you have perturbations, also these perturbations propagate more strongly into the performance of the algorithm. And what our tuning method does is to provide your trade-off between these two properties or these two behaviors. Now, if we come back to our inertia estimation problem, and you look at the setup, then you can hopefully see that this is exactly the setup that this consensus and innovations approach is tackling. So what we have done, therefore, is to take the C+I algorithm and apply it to this particular problem. And I would like to show now how it performs on the IEEE 39 bus system, which we have divided into 3 areas. So the IEEE system is like a standard benchmark model that is often used, or benchmark system that is often used in power system studies. And we have divided this now into 3 different areas that you can see also here highlighted in different colors in the topology on the right. And it also corresponds, of course, to this schematic illustration that I showed you afterwards. So we have 3 different control areas with 3 different system operators. And what we have done now is to optimize the gains of the algorithm using the result from the previous section. And this is now a simulation result under sort of ideal conditions. So we don't have any noise or other type of perturbations. But what we have is or like the only thing we have is usual load variations, as you would experience typically in power systems. So this implies we have frequency variations of plus minus 0.05 hertz. And you can see that this is already sufficient for the estimator to converge to the correct inertia value. So this is for area 1, this is for area 2, this is for area 3, and this is for the overall aggregated system. And you can see that in all 3 cases, indeed, not only the local inertia constant is estimated correctly, but all the different TSOs, or like the different agents, can correctly estimate all the inertia constants of the different areas in the power system. And we have here, like that's around 30 seconds, I think, also a change in the inertia constant in area 1. And again, the algorithm is able to identify that and to track the new inertia constant. And this also works even though we have simulated or implemented a loss of communication between area 2 and area 3 after 5 seconds. And in this charts, you see the same type of setup, but now with noisy measurements and with a time-varying inertia in area 1. And you can see that even in this setting, the performance of the algorithm is very satisfactory. And what we have done more recently is to now move the algorithm also into an experimental setting using the power hardware and loop facilities that we have set up at our lab here in Cottbus, where we now have a purely converter-based scenario or converter-based setup. And we use 5G communication to enable the distributed communication between, enable and implement the distributed communication between the different units. So this is how our lab looks like. We have here 4 different power converters, and they have a power rating of 15 kVA each. And we can operate all of them using real-time computers. And we can actually modify the control loops down to the PWM scheme. And these different converters are now connected here to a power line emulation cabinet, or short PLEC. So this is a replica using pi equivalents of different power line or like distribution power lines, as you can also see here on the right, from different lengths. So for instance, for 15 kilometers or 20 kilometers and so on. And the 4 different converters now feed a common electronic load, and this is like a standard power amplifier. And the setup now has, I would say, different interesting characteristics that somewhat differ from the scenario that I described earlier on in the simulation. Namely, now what we have is a fully converter-based setting, so there's no synchronous machine, and 1 electronic load unit. And what we have done is to include, or sorry, not to include, but to control all the distributed or like the inverters of the distributed generators in grid forming mode. So meaning we control their output voltage by using the virtual synchronous machine algorithm. Right? So if you recall, when I introduced the center of inertia, aggregated frequency dynamics, I sort of claimed and mentioned that if you have converter-based units that are controlled with virtual synchronous machine algorithms or sync converter algorithms, so that in closed loop they mimic the behavior of a synchronous generator, then the methodology that we propose is also applicable. And this is something that I want to demonstrate now also with this application or like experimental example. And for the communication, we use our 5G private network that we have at the university, essentially because in real-world applications, this might be something if you have a microgrid with a large number of small-scale distributed generators, they would typically not have a wired Ethernet connection, but most likely be more easily to be interconnected using some sort of wireless communication technology. And nonetheless, we perform the behavior of the 5G-based implementation with that of an Ethernet connection network. Right, and what you can see here on the right is now the setup. So we use 3 of these different converters to supply and feed the common electronic load. And they now communicate via 5G. And we implement on the right-hand side now our C+I parameter estimator in order to estimate online and experimentally the inertia constants of the different virtual synchronous machine algorithms that are implemented here at DG1, DG2, and DG3. And these are now the results. So the scenario that we have tested is that the electronic load exhibits a progressive rise in the power demand, which is implemented by incrementing its current demand by 1 ampere every 7 seconds. And this also, of course, then leads to sufficient persistency of excitation for the estimation algorithm to work. And you can see here again the estimation of the inertia constant for the 3 different units. So this is for H1, for H2, and H3, as well as for the total inertia constant. And similarly, sorry, to the simulation example, we also have modified here around 70 seconds the inertia constant of the first distributed generation unit. And you can see that in both cases, so in the nominal one and also in the new modified inertia constant, the algorithm is able to online track the overall inertia constant, and in particular the variation of the inertia at DG1. And I would say interesting observation that we have made is that despite 5G having a significantly higher latency than Ethernet, that does not significantly affect the convergence rates, but in fact the convergence rates are similar. And as I mentioned, in all for all different DG units, the estimation algorithm is able to accurately identify the inertia constant as well as the variation in the inertia constant H1 that we have around 75 seconds. As an outlook, what we are currently working on is to also implement and test the algorithm for the overall interconnected European transmission system, where we have detailed simulation data that is provided by Petros Aristido, a colleague in the power systems community who is with Cyprus University of Technology and specializes in, well, among other things, I would say by now, in real-time simulation of power systems. And he has a very detailed model of the overall N2E area with over 1,000 generators. And we have used that model in previous work to derive an online estimation algorithm for power system inertia. However, that was assuming the standard setting that I mentioned in the beginning of the talk, so that you have information of the overall power system and you want to estimate only the total inertia constant of the system. We did not address the problem that I have presented here, or like discussed here, so that we have different transmission system operators, and each of these system operators wants to estimate the inertia constant of their own area. So this is ongoing work where we currently are evaluating the results, and hopefully we'll have a draft ready soon. And with that, I come to the end of my talk, and would just like to briefly summarize what I've been talking about. So I've shown you the development of a tuning algorithm that allows you to robustly design the gains of the C+I based distributed parameter estimation in the presence of disturbances. This has been cast and formulated in the sense of, like in the form of a semi-definite program that allows you to ensure that you have a certain A2 gain. And we have then used this algorithm to propose an online algorithm to estimate the inertia constants in multi-area power systems. And I've demonstrated or illustrated how it performs at first in simulation, and I think more importantly also in a power hardware loop experimental implementation in a purely converter-based setting and using 5G communication. As I mentioned, so currently we're working on the application of the algorithm to a large-scale power system. And of course, something interesting, or like a interesting extension of our tuning method, is to also consider communication delays. And last but not least, we're also interested in applying the algorithm for cooperative control and estimation tasks in district heating networks. That may not be that relevant in your area currently, but if you joined early enough, I was just saying that we have around -5, -10 degrees at the moment in Cottbus. So heating is definitely important. And one of our key challenges as well is to decarbonize the district heating sector, because traditionally a lot of the district heating that we obtain here in the area is essentially waste heat from the large power stations. And of course, once these power stations are shut down, also their exhaust or like waste heat is missing. And we need to find new climate-friendly technologies and ways to provide heat to the different customers here in the area. And last but not least, to conclude, so the online inertia estimation is one of the areas that we have been addressing in the context of dynamic state and parameter estimation in power systems. Another topic to which also Nikolai has contributed quite a large portion during his PhD work is on dynamic state and parameter estimation for synchronous generators, where we have derived a number of different algorithms considering different levels of detail for the generator model. And together with colleagues from 50 Hertz, with René Suchantke, so 50 Hertz is our regional transmission system operator. We've also obtained experimental data from a large-scale power plant here in Germany that's connected to the 410 kV level, and we've been able to implement and validate our estimation algorithm also then experimentally. Yes, with this I would like to conclude, and thank you very much for your attention. Of course, I'd be happy to answer and discuss any questions or comments that you may have.
Thank you, Professor Schiffer, for your presentation. We open the question session. Remember that you can ask directly the speaker here in the Zoom session, or write down your questions in the chat, or if you are watching us in the YouTube broadcasting, also you can write down the questions in the chat of the YouTube page. So let's begin with the question session. Go ahead. We have enough time for some questions. I don't know if Professor Schiffer, it's okay to ask questions also in Spanish for you, or?
Sure. I mean, you can ask them in Spanish. I can try to answer them in Spanish too.
Okay, so tenemos la facilidad de que puedan hacer preguntas en español también con el profesor Schiffer.
hi.
Gustavo,
Maybe,
adelante.
well, I'm more interested in your opinion about the challenges in the transition, in the energy transition in Germany. I would like to hear what you can say about that from your perspective, at least in the region of Lusatia, and what are like the main problems you are trying to address with the IHZ. If I remember correctly, you were working also on multi-energy systems.
Yes, that's correct. So we are working on one hand on electric power system problems, and I think there you face probably like two different challenges, especially also here in the area, because on one hand we of course lose a large amount of large-scale traditional generation in the next years, that also was able to provide a large amount of very flexible, but rather flexible and reliable frequency support, both in terms of the inertia, but also in terms of primary control, for instance. So I think that's one challenge that area, and in particular the transmission system operator, is facing. And another one is that Brandenburg is the region in Germany with the highest renewable energy production. So we also have often the problem that we have a surplus in renewable energy production and need to somewhat be able to then transport and balance that generation with the demand we have in the area. And in that context, for instance, work that goes in the, or like new ideas that go in the direction of securing dynamic stability problems or like dynamic properties in power systems are definitely relevant. So for 50 Hertz, for instance, now these online estimation algorithms are actually of interest. When I presented them to them at first, like 3 to 5 years ago, their main take was that this is not relevant for continental Europe because we will have sufficiently many large-scale power plants that provide inertia. So this is one of the challenges that we address on the electric sector. And I think another one that is really crucial for the overall energy transition in Lusatia, but also in Germany and Europe at large, is heating. So if you look at the moment, a fairly large amount of our net energy consumption is dedicated to heating purposes. And this is very difficult to decarbonize because essentially it's always based on, like traditional heat generation is always based on fossil fuels. And so the only realistic way for decarbonization, I would say, is to do it via electrification. And that, of course, then poses additional challenges because you need to couple, or like you will have a very strong coupling between the electric sector and the heating sector. And this is something that on one hand needs to then be managed, where you also need to have suitable market tools and approaches, but also which needs to be addressed from a technical point of view, because of course it will place a very high burden on the electric power system infrastructure, especially during the winter season, right? And at the same time, what we are looking into is, for instance, how we can harvest or release flexibility in terms of storage provision that this can provide. And so one issue I think system operators worldwide have in the renewable energy transition is that the volatility in the generation, and that you therefore need storage capacities to be able to balance consumption and generation. But if you want to do that purely on the electric side, it becomes very expensive and also technically complicated to implement. And the idea here is, for instance, to use thermal energy storage to buffer excess in electricity generation, because the dynamics of thermal processes or like of district heating networks, for instance, are much slower than the ones you have on the electric side. And you could also use, for instance, part of the inherent storage that you have in the water pipes that transport the warm water to the different customers as an intrinsic storage in your system. And that, of course, then naturally leads to sector-coupled energy systems, where you need to look into the interaction between the electric system and the district heating system.
What challenges did you address to minimize or overcome the power ups and downs that are inherently part of renewable energy?
Oh, so I would not necessarily claim that I myself addressed necessarily that issue. I think one way to at least address it in the middle and northern part of Europe is to try to provide storage capabilities that are not purely electric, but that can, for instance, be heat or that can be hydrogen, and that help to balance in the long term variations in the renewable generation with the demand, right? And I think in the short term, of course, you often have battery-based solutions. And what we are working on as well is try to have like algorithms that provide a more flexible load behavior, so that you can, for instance, also adjust the behavior of certain large-scale industrial plants and their production chains or production processes to a higher variability that you have in the electricity generation. Right? But I think this is, at least from our side, most ongoing research. So I would not necessarily claim that I have contributed to solve any of these challenges yet in an actual real-world application setting.
Okay, one question more, please. Why using 5G communications? Why? How?
That's a very good question.
For
I would say
power
that
Hawaii in the loop outdoors.
the direct answer is, so I think in general, what of course we were interested in is if you have a setup that you can interpret as a local microgrid. So it's a system that is composed of a variability or like a variety of small scale distributed generators. And you want to still be able to, for instance, estimate certain parameters in the system, in our case, the inertia constant, that it would be difficult to require that all of them have a wired connection between them, but that it would be more easy to do this by deploying wireless devices. And then what you would want to have is, of course, a wireless technology that is fairly robust, reliable, has low latency, and also a high degree of security. And I'm not a communication expert, but from what I understood from people that we are working with, 5G is, at the moment at least, the technology that can provide these different properties, and therefore is quite suitable for this type of real-time implementations.
So mainly for securities.
Well, security, robustness, reliability, and also delays.
Okay, thank you.
So like you have a fairly secure protocol, but you also have a very, like a fairly robust communication architecture.
Okay, thank you.
But of course you could also use 4G probably, and it would still work because the amount of data that we are sending is not significant, right? So it's not like any large scale video images or anything like that that we try to transmit and analyze in real time.
Okay, thank you.
Okay, anyone else? We have time for one or two questions, more questions. Okay. Okay, Professor Dorado Ramos, go ahead.
Sorry, I'm just curious. I don't know whether my question makes sense or not, but I've seen that all the algorithms that you described are linear. Are there any non-linearities in the system that need to be taken into account, or is this satisfactory?
Let me go back to. So that's a very good question. Thank you. So in our case, what we do is to derive the regressor from the aggregated center of inertia frequency dynamics, and they happen to be linear.
That's fortunate.
You could, of course, argue that you want to model the swing equation more accurately, and that would mean that you would replace the active powers here by the torques of the different machines, and you would divide here by the frequency. Then you would get a nonlinear ODE, and as a consequence also like a nonlinear problem that, however, you can still cast in the standard form where you have a linear regression equation, because the parameter that you want to identify enters linearly in the dynamics. So therefore the estimation problem ends up being linear again. We have done this in the work that I mentioned at the end, where we applied an inertia estimation algorithm for the overall interconnected European transmission system. But since the frequency deviations are very slow, very small, usually, at least in our experience, this linear approximation of the swing equation works equally well.
Thank you. Thank you very much.
Well, with this, we end the seminar. Thank you, Professor Schiffer, for your presentation. Very interesting, and for accepting the invitation to participate with us. Thank you.
Thank you again very much, and thanks a lot.